In this section, we will be looking at the components of a UV visible spectrophotometer. In every UV or visible spectrophotometer, there will be a light source, a wavelength selector or monochromator, a sample compartment, and a detector. So first, let's take a look at the light sources. The light source is not just any ordinary light bulb. Special lamps must be used in order to get a high quality light beam. An ideal light source for the spectrophotometer would be a light source that can emit an intense continuous spectrum across the entire region, meaning all the wavelengths in the UV and visible spectrum. The light source should also have a long lifespan. There are three types of light sources that are commonly used in UV and visible spectrophotometers. Deuterium lamps emit light with wavelengths of about 185 to 400 nanometers, so it is often used as a UV light source. Tungsten halogen lamps emit light between 350 to 3000 nanometers, so this will be used as a visible light source. Xenon lamps emit radiation between 185 to 2500 nanometers, so this covers both the UV and the visible range. So a UV visible spectrophotometer may contain a deuterium lamp plus a tungsten halogen lamp. So the deuterium lamp gives the UV light and the tungsten halogen lamp gives the visible light. Or some spectrophotometers contain a xenon lamp, which can give both the UV and visible light. All of the light sources will produce a broad spectrum white light. However, in UV and visible spectrophotometry, we often want to select a particular wavelength. So to narrow the light down to a selected wavelength band, the light is passed through a monochromator. Ideally, since we are looking at a very particular wavelength, we would want the output from the monochromator to be a light of a single wavelength. But in practice, the output is always a band of wavelengths. For example, we might want to select a wavelength of 254 nanometers. However, the output will be a band of wavelengths, for example, 254 plus minus 10 nanometers. The monochromator has three basic components. First, we have the entrance slit. So this is where the light comes in to the monochromator. The light then hits the dispersing element, which would separate this light into its component wavelengths. The light of a particular wavelength will then exit the monochromator through the exit slit. A monochromator may also have some mirrors to align the light. When the wavelength is set on the instrument, for example, you key in a particular value, let's say 254 nanometers, then the dispersing element would be rotated so that the light of the correct wavelength goes through the exit slit. The dispersing element in a monochromator may be a prism or a diffraction grating. I'm sure you all know what a prism is. The prism, it would be made of glass or quartz, and when light strikes the prism on one surface, the light will be refracted, and the light that emerges through the other face will be dispersed into the different wavelengths. Diffraction grating is actually more commonly used in spectrophotometers. The diffraction grating is a highly polished mirror that has a large number of very precisely cut parallel grooves. So when light strikes the surface of the diffraction grating, the light will be diffracted and dispersed into its different wavelengths. After the light has been narrowed down to that particular wavelength, the beam of light now passes into the sample compartment, where the sample is held in a cuvette. The cuvette will be placed usually in a spring-loaded holder, and the sample compartment is usually black so that it can absorb any stray light, and it has a lid which should be closed to prevent stray light from coming in. As you have seen in our labs, Some instruments are single beam spectrophotometers and some are double beam spectrophotometers. This diagram shows the difference between a single beam and a double beam spectrophotometer. So basically, in single beam instrument, there's only a single light beam that comes out from the monochromator, and that single beam will pass through only one sample before it's detected. Whereas for a double beam instrument, the light that comes out from the monochromator is split into two beams that are parallel to each other. One will pass through the sample and the other will pass through a reference or the blank. Then both beams will be detected by the detector. So again, for a single beam spectrophotometer, the light beam that comes out from the monochromator will pass through only one cuvette, so that's the sample in the cuvette, and it will get detected by the detector. Since it has less components, this will be a lot less expensive compared to a double beam spectrophotometer. But the downside is it may be less accurate because it cannot correct for fluctuations in the middle of the experiment. For example, the light intensity may change during the experiment. It may fluctuate a bit, or there may be fluctuations in the sample's absorbance over time. A single beam spectrophotometer must also be pre-calibrated with a blank before use, and you all are very familiar with this. Before you put the sample in, you must first put the blank in and press auto zero on the machine. In comparison, in a double beam spectrophotometer, the monochromatic light that comes out would be split into two beams that are parallel to each other. There are also two cuvette holders, one for a blank and one for a sample. Double beam spectrophotometers are more accurate because the sample measurement can be corrected for any instrument fluctuations in real time. Let's say during the experiment there is some slight fluctuation in the intensity of the light source. In a single beam spectrophotometer, it might be wrongly recorded as an increased absorbance when actually the problem was with the light source. But for a double beam spectrophotometer, since there is always a comparison with a reference cell or the blank, then any fluctuations would be corrected for immediately. Now let's take a look at the cuvettes. There may be different types of cuvettes for slightly different purposes, but all cuvettes would be standardized to have a path length of 1 centimeter. Cuvettes that are used for visible light could be made of glass or plastic. Glass is cheap, about $5 each, but the cuvettes are breakable. Plastic cuvettes are made of polystyrene and they are very cheap. These are not breakable, but they can get scratches, so these are disposable cuvettes. On the other hand, cuvettes that are used for UV light experiments could be made of quartz or fused silica. Both of them are very expensive and they are also breakable. Previously, these were the only options for UV spectrophotometry, but nowadays, disposable UV cuvettes are also available. If two or more cuvettes are used, for example, one for the sample and one for the blank, then these cuvettes need to be matched. Matched means that they are identical in path length as well as their reflective and refractive properties. Such cuvettes are sold as matched sets. Cuvettes must also be clean and scratch-free because any scratches or any dirt on the surface would reduce the transmission of light. After the light passes through the sample, it then reaches the detector, which will convert the light into an electrical signal. There are two types of detectors that are often used in UV visible instruments: photomultiplier tubes and photodiodes. Just a fun fact, since these are light sensors compared to heat sensors, which are used in infrared spectrometry, we call UV visible instruments spectrophotometers. So photo means light, while infrared instruments are called spectrometers since the sensors are not really detecting light. This diagram shows what a photomultiplier tube is like. It is a light sensor combined with a signal amplifier. When a photon comes in and hits the electrode, an electron is released. And you can also see that the signal is being amplified. There's more and more electrons being released until it reaches the anode. The ability to amplify the signal makes this a very sensitive detector. Another type of light detector is photodiode. Photodiodes are semiconductors such as silicon, which can convert light into electrical energy. This is a photo of a single photodiode. Multiple photodiodes can also be put together and assembled into arrays. This photo here shows a photodiode array, or it's abbreviated as PDA. For instruments that use a photodiode array detector, the design of the equipment is slightly different. Take a look at the diagram. In this design, instead of having a single wavelength pass through the sample in the cuvette, all the wavelengths from the light source will pass through the cuvette. When the light passes through the cuvette, some of the wavelengths will be absorbed by the sample. The light from the sample then reaches the monochromator and the light is diffracted. The PDA detector is able to capture all the wavelengths at one go, and this enables us to simultaneously measure the absorbance at different wavelengths by the sample.